This is getting heated back here. This is getting heated back here. I like this. I like this. So how we measured variation? Harrison, give me what's on your mind.
It's part of the
I took the max and min of Ernie.
Yes.
Figured out the difference. And it was only like 4.
4.
And then for Bert, it was 39.
yeah.
Skylar mentioned something called the range. That's actually called in statistics the range of the data. I love that. And it's cool that you, it sounds like a couple of you also thought of that. Just find the distance. I love that. I love that. So the range of the data is just the high value minus the low value. So for let's make a secondary list here for Ernie and Bert. Ernie and Bert. We'll measure Bert as a mean, right? Yeah. Bert. Range. Okay. Ernie's would be 83 minus 79. About 4. Or 4. Bert's 100 minus 61. 39, which is essentially 40, which means Bert is 10 times as variable as Ernie. That's crazy. I agree. I totally agree, JC. Totally agree. It's insane to think about that. Range is not used all that much in reality outside in data sets. Can anybody think of why range might be misleading? Because what JC just said is 100% accurate. Oh my God, he's 10 times as variable? Yes, it is. He's 10 times as variable. Robert?
You have a huge outlier.
Yes, the problem with range is it ignores the rest of the data set except the extremes. So let me ask you a question. Suppose Bert's test scores were 100, 99, 197, and 61. What would his range be?
39.
Exactly the same thing, 39. What would his average now be?
Would be higher.
Much higher. As would his median, still wouldn't have, well, I guess we'd have a mode of 100 then, as I said 100 twice, didn't I? So the problem with range is it doesn't look at every single data point. I love the measure as a measure of variation, but because it ignores most of the data set, all but 2 points, it can be a little bit non-indicative of the rest of the data set. Harris, what do you think?
So it's test scores though, so it's not like accumulation of chapters or something they're supposed to have learned?
It could be, depends on the instructor. I don't give cumulative assessments, a lot of folks do.
Okay, so theoretically though, but like, because you take a bunch of different tests, the tests are, in theory, formulated kind of the same.
That's all, the only assumption I'm
A
making.
series of questions, added up.
Sure.
But he has to get a bunch of those questions wrong to get a 61. Like, consistently wrong.
Yes.
And
What are you getting at?
So, the 61 wouldn't be as big of an outlier if you think of it like that. Because he just might not have got like chapters 3, 4, and 5 or something, whereas Ernie did.
Or if you think of it as a sum total of correct responses over the course of a term, they both did exactly the same. Because whatever Bert screwed up with on the 3, 4, and 5, he made up 4 on 7, 8, and 9.
Okay.
Because they all balance out to the same number of correct questions because they have the exact same average. The question is, how do we measure that sway from knowing a lot to knowing very little? I see what you're saying, Harrison. Totally agree. The problem with these two guys is they balance each other out.
Perfectly. The other way.
Perfectly. That's why the problem with these 81s, they perfectly balance. I love what you're saying, though. What you're saying. You two guys were getting into it when I came back in the room. What was your discussion about?
I was just laughing at her.
Oh, okay. That's terrible.
I said that 60% of the time, Bert will score an average of 92% or higher.
There we go! So one way of looking at it is using these as an indication of some kind of a relative percentage. I'll call it the relative percentage. Relative percentage. And you can, and the problem with this is there's infinitely many ways to define it. For example, for Bert, Hattie says 60. What did you say? 60% of the time.
He'll score 92% or higher.
How'd you get 60%, not 40%?
So 60% of the time, if you take the mean average of his 3 highest scores, 60% of the time, his mean average will be above a 92.
But you're conveniently ignoring the 68 and 61 by doing that. So, can I change it?
Yeah, absolutely.
How about I say 40% of the time, historically, he has a test score greater than or equal to 94%. How about that?
Okay.
That way, because that's true. I mean, of the 5 test scores he has, 2 of the 5 are at least 94. Now, this of course is assuming that he continues that behavior, and it's exactly patterned after that. JC, what's up?
But it's different. So finish your thought and then
Shouldn't
I'll...
that be on?
Damn it!
On Bert?
40%. See, I screwed myself. I switched them now. 40% of the time, his test scores are greater than or equal to 94. Thank you. Sorry about that. If I confused anybody, I apologize. JC, go ahead.
Okay, so if you're saying that range isn't used all that much,
Yes.
I need an example for when it would be used.
Go ahead.
I'm thinking about, so let's say these were two of your students and it's the exact same test. And you're wondering why there's such a difference in them. So you're doing the in-class test and then you switch to take-home test, but some people do better in class versus out of class, and then you come up with like the half in class, half take-home. So would you use range for something like that? Or when do you use it?
I don't use range, and unfortunately, you don't use it for inferential discussions. And when I say that, I don't use range when I have to take a sample of data and then make a decision about a future data set based on that. I do use range when I'm setting up graphical displays of descriptive data all the time. How many bars should this thing have in it? Well, what's the range of values? How far is that range spread? And I want 10 bars, therefore I've got to divide the range by 10 to figure out how wide. So I do use it in that respect. What I don't use it for very often is conversationally describing the inconsistencies from a data set to the other. We have a better measure for that, which we're working towards. You guys are getting damn close to it already. Does that make sense, JC? So I'm not saying it's useless. I'm saying I don't use it very much for this right here. I use it more for descriptive use than inferential use. Thank you for that. Very, very good. Harrison, go ahead.
So I think Bert had a Monday-Wednesday class.
Assume everything's the same. I see, you guys are getting close. You guys are getting close to that whole, like, I'm trying to read too much into the data. Bert was totally hungover. You don't know that.
Came on Monday.
You thought that. It might be, but we don't know that based on all we have are these numbers. All we have are these numbers. So do you see how we can do that kind of a percentage thing with Bert and Ernie? And there's probably infinitely many you can do. I mean, for Bert, you can say 60% of the time, he gets at least an 82. Right? Which is actually technically a little bit better than Ernie. Because Ernie can only claim that 40% of the time he gets better than an 82, or equal to an 82. But Ernie can also claim that 100% of the time he gets between 79 and 83. And Bert can claim that 20% of the time he gets between 79 and 83. So, I mean, the problem with that, you can see right away, is they're all right, but they're so vacuous and vague that they might not tell you a whole lot. So, good. What else do you guys come up with? That's about it. It's tough. It's tough. You guys all learned how to take an average, probably very... Oh, Michael, please, go!
I was going to say, you could kind of do a histogram for it, do anywhere from... They got a score between 60 and 65, 65, 70, and you can do this in the same way.
I love this. Create a histogram and get a visual of it. So, if you were to do that, let's do a real quick histogram here for Ernie and Bert. Okay, and Michael, you said to break it by 5s, it sounded like?
Yeah.
So if you got 60 here, 65, 70, 75, 80, 85, I think we'll do it for Ernie, right? Okay, so Ernie, his scores all exist between 79 and 83. So actually, technically, he's got like 1 bar here, and then the rest of the bars here. That's what Ernie's histogram looks like. What's Bert's going to look like? Well, it's got to go a lot further. His are going to look more like this. Something along those lines, or maybe 5 evenly heighted ones, kind of spread out like that. Now that's a fantastic way of looking at the variation. But the problem with that, I think, did I mark this scroll up again?
No.
Okay, go ahead.
I think we need to change the names to Kate.
That's when I do it. That's when I start reversing Bert and Ernie. That's possible. It's possible. Patty, Kate, Ernie, Bert. Oh God, you're in my head now. It's freaking me out. So the problem with this, Michael, is I said, what was the width you said? You said 5. 65 to 70, 75 to 80, 70 to 75. Suppose you collapse it down to groups of 20. 0 to 20, 20 to 40, 40 to 60, 60 to 80. You're going to lose a lot of that precision. And that's the part, I don't want a measure that's based on somebody's decision about precision. I want a measure that's kind of uniform, if that's fair. I love what you're saying, and I'm not saying it's not a great way of visualizing it. Just like I'm saying, I love this. I'm not saying it's not a great way of talking about it, just like I'm saying I love this. I'm saying I want kind of a standard measure is what we're kind of shooting for here. Hattie?
What about like a bell curve and standard deviation?
Well, number one, we don't know if we have a bell curve or not. Based on this, it doesn't look like we have either a bell curve. Now, you just mentioned something, Hattie. I can't help but notice. I heard you mention the word. I want to slide this down. No, I gotta clear it off, that's what I gotta do. Let me come over here. Can I remove this? Is this okay? Remember that Ernie's average is 81 though, we're gonna need that. All right. Hattie mentioned two words used together that I really want to get into today. The most important measure of inconsistency versus consistency that is used by statisticians today is called standard deviation. Now, it's called standard deviation because essentially it is the standard for measuring deviation, okay? Standard deviation. And that's the one. Hattie, what do you know about it?
It's used a lot in, or the connotation that I know it in is in psychology.
Mm-hmm.
So talking about like how one group of people varies from another group of people.
Good. So essentially, if they vary, this standard deviation is a number. Kind of like an average. The average is a number, the median is a number, the mode is a number. The standard deviation is also a number. And essentially, the letter that we use to stand for it is just little s. And we'll come back to him. We're going to show you how we're going to get him for Ernie here in a second. What do you think in your gut? An inconsistent data set versus a consistent data set. If this thing is called standard deviation, do you think an inconsistent data set should have a larger standard deviation or a smaller one? Got a little bit of dissonance there. I heard larger, I heard one larger, because Scott's sitting right next to me, I heard her say larger. So for measuring deviation, deviation means moving away from center, moving away. So do you think inconsistency should be larger? Yeah, that's how it's set up. So basically, the takeaway on standard deviation is larger S means more varied. Smaller S means more consistent. Anybody figure out why I put larger and smaller in quotes? Anybody think of why I put larger and smaller in quotes? Is 2 larger than 1? I'm not trying to be a trick question. Is 2 larger than 1? Is 10 larger than 1? Is 100 larger than 1? If you compare 100 being larger to 1, does 2 being larger than 1 seem as impressive anymore? No. That's why I put larger and smaller in quotes. It depends on what larger is defined to be. But I'm talking about this from a purely mathematical standpoint. I want a number that will come out bigger for Bert than it will for Ernie, because Bert is more varied. Is that fair?
Yes.
Bert is more varied. I want Bert's value of S to be bigger than Ernie's value of S. And when I say value of S, S is going to be one more of those statistics, like X bar, like the mode, like the median. It's just a number that pops out. But the meaning is what I want to make sure we understand before we walk out of this room today. That's what I want. Now, the reason I bring this up, I'm going to erase some of this if it's okay, guys. I mean, it's on video, which is nice. It's not really going away. For better or for worse, YouTube has my face plastered all over it. Hi, everybody! Every video starts the same. The technical phrase of standard deviation actually has a few more words that very rarely gets spoken. It's standard deviation around the average. Technically speaking, the standard deviation is measured as deviation from the average. That's the definition of it by textbook. We very rarely call it that. We call it standard deviation. But the definition, the construction of the standard deviation actually comes from the average, believe it or not. So to help us understand this, I've created a little graphic. I've got it up on the screen here in a sec. Let me swing this over. This will hopefully help us understand this. Voila! Michael, your histogram-ish. Just your dot plot. I made a dot plot, kind of like Michael was telling me to do, but not really. I kind of bastardized it a little bit. So, what I've done is I put a little head for each of the test scores of Ernie and Bert. Okay? Bert's the unibrow, Ernie's a little round-headed guy. Okay? And what I want to do next is I want you to understand what that dotted blue line is up there. What's that? That's the average. Notice how it's the same for both of them because they both had an average of 81. Now, how are we going to use that diagram to help us figure out, oh, JC, what are you thinking over there? Go, my friend.
It's the average, so that's like the middle, and then you deviate out. So
Good.
that's where you start your, yeah.
I love what she's saying. She's saying 100% correct. What we're going to do is we're going to create a little chart. We're going to create a little chart, keeping track, and the way you're doing with your hands is perfect, JC. You're saying you deviate out. We're going to keep track of those deviations. Well, let's do Ernie first. For Ernie, okay, I'm going to make a laundry list of his exam scores first. So the first thing I'm going to do, I can't do this in my head, JC, which is why I want to write it down. I can't keep track of all those deviations, especially when we get the burnt to get ridiculous. So I'm going to write down Ernie's exam scores. He's got an 81, looks like he's got an 82, 79, 83, and an 80, I believe, right? I think those are his exam scores. Okay. Deviations first. Now, deviations from mean is just a fancy way of saying differences from mean. Wait, difference from mean. So I'm going to take each exam score and subtract the average in each one. Fair enough? So 81, exactly, it's 0. There is no deviation. It is average. So that deviation is no deviation. 82, positive 1. 79, negative 2 because it's below average by 2. 83's up 2, 80's down 1. This is what JC was indicating with her hands perfectly. The deviations from the average. Come here one more time. No, right there, yeah. Megan, thank you. You're looking at it, and I saw the way you're looking at it. You're looking at it, you're kind of processing. What are you thinking about?
Isn't it just 0?
Because the first thing I'd ask you to do is we now have JC's deviations. If you sum those deviations and divide by 5, what do you get? 0. Guess what? If you take any data set at all, and do what we just did, it's going to sum to 0. As a matter of fact, I think this is so cool. I made a video for it, which you'll see linked off your homework page for next class. And it's also an extra credit problem to prove why. Kate, what are you thinking?
Isn't that the definition of the average?
No, not the definition of the average. It's kind of the fair share idea, but we never proved it. I mean, the definition of average says it's the amount you would have to give every data set to have the same amount while summing to the same total.
Well, that's saying that the difference then between the numbers and the average are going to balance out. That's kind of...
It doesn't say that mathematically. It implies that.
Okay.
And we imply that by putting our pen there, which balances. But it's nowhere near as obvious in Bert's data set as it is. In Ernie's, I think it's completely obvious. I mean, there's a -1, a +1, a -2, a +2. It's not as obvious on Bert's, because it's not as symmetrical. What I'm saying is this, even with lack of symmetry, this works for any data set. Hold that thought, we'll come back to it. JC?
So, it'll depend once we do Bert's, but for all of them being 0,
Yes.
and then like his numbers are smaller, so when we do Bert's, I think they're going to be bigger, so you can see the variation.
The negatives will be more negative, the positives will be more positive.
That's what I'm saying. So you could, but it's a wider range.
It's
right?
perfectly said, JC, and it's the problem with this column. This column doesn't do the job we need it to do. I would love to average that column and be done with it. But if for every data set we average that column and get 0, that doesn't tell me anything.
All this says is that when we do the graph, you're going to see less of a range versus a wider range.
Right, but it doesn't talk about the standard deviation. It doesn't include the average. So here's how we fix it. There are a number of ways we can proceed right now to fix it. One is to take the absolute value of all those and add them up and average them, which is, Excel has a command for that called avdiv. We'll get into that in your take-home as well. But this guy, the one that Hattie mentioned, does this move. It takes those values and squares them. I'll explain why momentarily. So we're going to take all those and square them. 0, 1, 4, 4, 1. Now somebody remember that we squared everything. Because at some point we're going to have to unsquare it to get rid of that. Megan, you're elected. You remember. That right there, each of these values is the squared deviation from average. If we add those up, we get 10. That is called the sum of the squared deviations. Sometimes if you're reading journals for psychology, sociology, HDFS, natural resources, you'll see the acronym SS for sum of squares. That's what they're talking about. Some of them still use that derivation or that acronym to explain variation. Say it again, JC.
It's the sum of this.
Some of the square deviations, SS or SSD, I don't like using just this because of a unit problem. And the unit problem I'm talking about is, we're talking about points on an exam right here. Points on an exam. What is the unit down here now that it's been squared? Points on the exam squared. I don't know what that is. What is a squared point? I mean, it seems like it's better than itself by itself. It doesn't make any sense. So that's why I said, Megan, keep track of the square root. We're going to have to deal with that square root. That'll get us back to points eventually. Now, the problem with this is the sum of the squared deviations across all of Ernie's data. Okay? I want to get a measure of a standard average deviation, if you will. So I want to average this out. This is the one thing I don't have a perfect answer for you for right now. I will, I promise I will. It's one of those goofy things in statistics that doesn't lay in order properly. I want to divide this. What's the logical thing to divide this by in order to average it out?
5.
5, correct? Because there's 5 data points. You actually divide by 1 less. You divide by 4. Weird. Weird. Now there's a reason for that. It's called degrees of freedom. Another reason for that called the central limit theorem. All of which doesn't make any sense to you right now at all, and I'm going to hide that from you as long as I can until you're ready to hear it. But for right now, and realize you're never ever going to have to write this formula down again. You take the sum of the squared deviations and you divide by 1 less than the sample size. I can sense the vomit right here, right about your Adam's apple. I know this. I see it every term. I apologize. Just realize that if you can deal with the next minute and a half, you'll never have to do this by hand again. Just trust me on this, okay, friends? Trust me. This right here is actually called S squared, or the sample variance. But we still have the same problem we had before, because it's still squared. But numerically, what it's going to be is 10 divided by 4, which is what, 2.5?
Yeah.
2.5 what's?
Units squared.
Points squared, units squared, right? We're still squared. Megan? What do I gotta do? Take the square root of that monstrosity. If you take the square root of that, you get S. The square root of 2.5, which is about, was that 1.8, 1.7? Then we gotta square root of 2.5.
1.58.
1.58? Oh, 1.6. 1.6 what? Points, units. No longer are things being squared. Thank you, Megan, for reminding me. 1.6 points. So what we now have for Ernie over here, is we have a standard deviation of 1.6 points. A standard deviation of 1.6 points. Now, time out. Deep breath. That's a lot of algebra.
We're programming the calculator.
Yes. However, the calculator hides this column and doesn't explain why we have to go through this song and dance. It just vomits a number out.
Yeah.
And I hate that. I mean, I love that. I take that back. I love that. Sorry, YouTube world. I love that. But I hate you guys not understanding what's going on in the background for something like this. You have to know what's going on. And more importantly, the calculator doesn't tell you what that number means. We have all these meanings. We have these meanings for all these numbers. The average is the fair share, is the share measure of center. The median is the geographical location measure of center, as Robert pointed out. The mode is the most measure of center. What is the standard deviation? It's a measure around the center. I love it. Give me even more. JC, what's on your mind over there? Where can I put this? I'm going to put it.
Seriously.
Oh, I've seen this before.
You have? Oh, good. Let me hear it. Let me hear what you've heard.
Oh, I don't remember this one part. So, if the standard deviation is 1.6 and standard deviation is around the average, so we have two thoughts. It's either going to be 1.6 altogether between, with the average in the middle.
Good.
You're going to take half of that and do half on one side, half
I
on
love what
the
you're saying.
But I don't remember.
Plus or
which
minus.
one.
I'll tell you what. I love the plus or minus.
Yeah, that's
Brittany.
Heather.
Heather, where's Brittany? There's no Brittany in this class.
Uh-oh.
There's two in the other one. That means on average I have one per class. Damn it. JC, I want you to hold that thought till this class. The idea of the plus or minus. Heather, the plus or minus is crucial.
Yeah.
Is crucial, but it's too specific. to a certain kind of data set, which I want to come back to. Just give me till the next class. I want to give a more general definition of what this is. Who's heard of standard deviation? You've heard of it before? Scott, you've heard of it before? Give me what's on your mind about this. If you had to tell me what the 1.6 meant, what does it mean that Ernie has a standard deviation of 1.6? I didn't even pick on you if you were. I apologize. You can say it. You can defer if you want. Photo friend. That's okay, totally fine. Kate, go!
Would it mean that on average, Ernie's standard deviation, it would be 1.6 points from either side of the average?
Boom! Shirley, is that what you're going to say? You guys got it. That's the most intuitive way of thinking about standard deviation. The most intuitive way is S, or standard deviation. I know. Is that a bomb going off? Standard deviation is, on average, data points, whoops, are S away from the average.
Wouldn't it be 1.5 then?
Well, sure, I'm trying to make it general though, Michael. So for any data set, you're going to be S points away on average. Whether it's 1.5, Bert's will be more, whatever. We'll calculate Bert's next time. I think we're around the time today. So basically, what I'm getting at here is that measure of S is a measure of average distance from the average. You have to use the word average twice there. On average, you're that many points away from the average. So on average, Ernie is about 1.6 points away from his average. And you can kind of look at the numbers and get that. He's 0 points away, he's 1 point away, he's 2 points, he's 1 point, he's 2 points. If you average all that stuff up, arithmetically it comes up to 1.2. There's a difference between 1.2 and 1.6 because of this little destructive move in here with the squares. Michael, go ahead. Is that what you're going to say?
That's what I was going to say.
You were going to say, why don't you just average the distances? Michael brings up a good point. He says, why don't you just average the 2, the 1, the 0, the 1, and the 2, which are the actual distances from average. That's called the average deviation, not the standard deviation. And the reason, I'll give you the 30-second answer. I'll give you the 10-second answer. The average deviation is not an unbiased estimator. And here's what I'm talking about then. Here's what I'm talking about. When you do statistics, I want to pause this and go over to the sideboard to wrap the day up with this question, if that's okay, Michael. Okay. It's a fantastic